So welcome to today's lecture, the topic of which is coupled oscillators. Last semester we dealt rather extensively with simple harmonic oscillators, the prototypical example of which is just a mass of a spring. So we can take a cart like this and attach it to a spring, and the spring has spring constant K. The cart has mass m, and then we'll denote x, the deviation of the cart from equilibrium. So this is its equilibrium position. So if we have this situation, things are relatively simple. We know that we can have a force on the cart, and that force is just going to be equal to minus kx in this case. Force is linear in the displacement away from equilibrium, and by Newton's second law, of course, this is equal to the mass times the acceleration, or x double dot. Actually, I'm going to write this down here. It's equal to the mass times x double dot. And this simple differential equation has the solution that x of t equals some amplitude times cosine of omega t plus phi, where omega is the frequency and that is the square root of k over m. So this we know very well, of course. And simple as this is, it describes many systems quite well, ranging from molecules to elementary particles and to, of course, carts attached to springs. But it is still too simple to describe many things that are quite commonly occurring in nature. One thing that it has, which makes it really too simple for many applications, is that it's linear. The force on the cart is linear in a displacement away from equilibrium. One could, in principle, add some nonlinear terms here, and that would change the behavior of this rather dramatically in some cases. We may deal with this later when we talk about nonlinear dynamics. But it's also simpler in another important manner, and that is that it only has a single degree of freedom. There's only one cart, and it can only move in one single direction. And often when you have oscillating systems, they are a good deal more complicated than that. And this is really what we're going to deal with here. So to do this, just going to move this equation down here and delete this stuff to give me a little more room to draw. And when I've done that, I can extend this a little bit longer. And then we'll add in another spring, another cart, yet another spring, and a vertical wall there. So now we have two carts, and they in general have different masses. And we have three springs, and they in general will have three different spring constants. So this is a more complicated system, but the way we solve it is really the same as that of a simple harmonic oscillator. We have a cart. We have to look now at the forces on the carts. There are two carts. There's cart 1 and there's cart 2. So the force on the cart 1 consists of the force from the spring on the left. That hasn't really changed anything, except we have to add some subscripts. K1 and times x1 with a minus sign is the force from the left on cart 1. We also have a spring number 2, which gives you a forced component 2. Now, it is a little more complicated. It will depend both on the position of cart 1 and on the position of cart 2. And we're going to indicate the position of cart 2 with position x2, which is the deviation of, or the motion of cart 2 away from its equilibrium position. So the total force now on cart 1 from this spring will actually be equal to K2 times X2 minus X1. I hope that's pretty clear. Right? If X1 and X2 change by the same amount, then the force from the spring doesn't change. It's only the difference between the two that gives you the force, and you can then verify that the sign here is right. If I increase X2, then I get a positive force, a force towards the right on this cart. And if I instead increase X1, holding X2 constant, then the force decreases and might go negative. So that gives me a negative force. That is a force to the left, a pushing force on this spring onto cart 1. So that's now the force on cart 1. And we can do a similar thing for cart 2. Right? So cart 2 is attached to two different springs. There's a spring on the right with force K3, and then there with spring constant K3, and then there is the middle spring here again. Now, because of Newton's third law, we can immediately say that this force from this second spring is just going to be negative the force on the first cart. So what we get here is just minus K2 times X2 minus X1. And then we get the force from K3. And we can see that if mass 2 moves towards the right, that is X2 increases, then we get a negative force pushing towards the left from spring 3. In other words, that means that the force has to be minus K3 times X2. Right. So that's now what the force equation looks like. And the force now on cart 1 has to then, of course, be the mass of cart 1 times X1 double dot, and the corresponding thing for spring 2. And we can rewrite this as a simple differential equation. What we'll get is just m1 x1 double dot equals minus k1 plus k2 times x1 plus k2 times x2. So what I've done here, it's the same equation that we have down here. I just rearranged it so that I get the terms proportional to x1 together. So keep those together. And we do the same thing now for cart 2. So that gives us m2 times x2 double dot equals k2 times x1 minus k2 plus k3 times x2. And that's a differential equation that we need to solve. So this is now a couple differential equations. A differential equation in two variables, x1 and x2, the deviations of each cart away from its equilibrium position. And it's, of course, more complicated to solve it than to solve that of a simple harmonic oscillator. But we can solve it using techniques that you already know. To see how that might work, I'm going to now write a couple of matrices on a suggestive form. So let's say I'm going to introduce this matrix M. I'm going to do 2 bars above it just to indicate that this is a matrix. It has 2 dimensions. That's why there are 2 bars instead of 1 for a vector which has 1 dimension. So I write that M1, 0, 0, M2. And we're going to introduce a K matrix similarly. And it is equal to K1 plus K2 and minus K2 on the first row, and minus K2 and K2 plus K3 on the second row. Finally, we'll also have a regular vector x. That's a really ugly x. Regular vector x, not much prettier, but still, which is just a column vector that consists of the two variables that they're interested in. So if we made those definitions, this set of differential equations here can be written simply as M, matrix M, multiplies now the vector x, M double bar times the vector x double dot, equals minus matrix K times vector x. And you should verify for yourself that indeed what I wrote here is in fact completely equivalent. This equation here is completely equivalent to what you have up there. Now, if you just look at this equation, it looks suggestively just like the simple harmonic oscillator equation. And you might think that it can be solved in a very similar way, and at least the solutions should perhaps be on a similar form. So to solve this, we are going to try and leave the drawing in there. We're going to make an ansatz. And this ansatz is that, well, the motion of cart 1, basically x1 as a function of time, is going to have the same form as that of an harmonic oscillator. There's going to be some amplitude, which I'm going to call alpha 1 times cosine of some omega times t minus delta 1. And I'm going to say that x2 of time is some other amplitude, a2, times cosine of omega t minus delta 2. So that's my ansatz. So I have two different amplitudes, I have two different phase shifts, but both of these equations have the same frequency. So both of the oscillators, or both of the carts, are oscillating at exactly the same frequency. Okay, if this is a solution, well, if this is a solution, then an equally good solution is the following. Where I simply, instead of writing x now, I wrote y, but it still refers to the positions of the carts. Right? I call them either x or y, whichever. It's still the positions of the carts. And the only difference between these two solutions is that here we have a sine function and there we have a cosine function, and they're both really the same. The only difference between the two is where you set time t equals 0. So the reason I did that is because now this enables us to play a trick which we have used several times before, and that is to introduce z1 of t, which I'm going to say is just equal to x1 plus I times y1, and then I'm going to say that z2 of t similarly equal to x2 plus I times y2. Okay. And if we do that, then we get, just putting everything together here, we'll find that z1 of t equals alpha 1 times e to the power of I times omega t minus delta 1, and same thing for z2. Okay, so that's a little bit simpler. So that's the solution we're going to work with. And this, of course, happens just because the exponent of a complex number equals cosine plus I sine. Something you should remember. Just write it here for those who might have forgotten. I can write e to the ix equals cosine of x plus I sine of x. Something you should know without thinking by now. Okay, so just making this ansatz, we can write the sum of x1 and x2 like this. We can rewrite that a little bit. So we get alpha 1 times e to the I delta 1 times e to the I omega t for z2. And z1 equals alpha 2 times e to the I delta 2 times e to the I omega t. Now, what we have here is a real number, alpha 1, times a complex phase. So together that makes a complex number, which represents both the amplitude and the phase of the position of the oscillation. So I'm going to call this A1, and same thing here, A2 times e to the I delta 2 is A2. So that means that the solution can be written as A1 times e to the I omega t for z1, and A2 times e to the I omega t for z2. And like I said, A1 and A2 are known as complex amplitudes. Okay. All right. So so with this, we can now write z on a vector form, just like we wrote x on a vector form here, and we'll finally get that the solution we're going to try and work with is the vector z as a function of time, which is now equal to a column vector which consists of the two complex amplitudes a1 and a2 times e to the I omega t, or just the vector a times e to the I omega t. Vector a is just what we're calling the column vector that consists of a1 and a2. So it's important to note, though, that x and z, I've written them as vectors here. They're not spatial vectors in the sense that you're used to. It's not like they have an x component, a y component, and a z component that are perpendicular to one another. It's just a convenient way to write the two variables that we have here, the position of the first cart and the position of the second cart. They're two different dimensions, but they're not perpendicular to one another in the normal sense in any case. So this is now the solution that we're going to try to see if that actually solves this equation. And you can now see that actually this has the same general form as the solution to a harmonic oscillator. And this, just as the differential equation that we started with had the same form as the solution to a harmonic oscillator, simple harmonic oscillators. The difference is that this is now a matrix equation, and the solution now is a vector equation, not just a scalar. So the final step then is to see if z really is a solution to this differential equation, and that really just involves plugging it into it. Before we do that, though, I'm going to correct a slight error here, which involves adding minus signs here in the exponent because there are minus signs in the sines and cosines. Okay, to plug it in, first we note that vector x is just the real part of z. So if z solves the equations, so does x. So then all we really have to do is figure out what z double dot is, and that's obviously just equal to minus omega squared times z. So if we plug that into this equation, we will get matrix M times z double dot, but that's the same as z times minus omega squared, and this needs to be equal to minus matrix K times z. If we then substitute z explicitly, we get minus omega squared matrix M vector A e to the I omega t equals minus k a e to the I omega t. It's a vector there. And this we simply then rewrite as, you can see we can cancel out the exponents there, and then we rewrite this as k, the matrix k, minus omega squared matrix M, scalar product with vector A, because this is a scalar product or vector product, equals 0. And this you should recognize from linear algebra as an eigenvalue problem. And it's solved just like the eigenvalue problems in linear algebra, and this is what we're going to do in the next video.